Hi, Assalamualaikum and very good evening. My name is Muhammad Isham bin Hamizun and my matric card number is DE170094. Today I would like to present for my final year project SEM 2. Okay, my supervisor is Dr. Haziza binti Hassan and my both panel, the first one is PM Sitawa binti Ruslan and the second one Dr. Wasuzarina binti Mat Juwadi. First thing first, I would like to tell my title. The title is Design of High-Speed Fast Fourier Transform using Vedic Multiplication. We go to the next slide. What do we expect from this presentation is 5 sections. First one, introduction, which is the background information of the research. The second one, literature review, other resource relevant to area of research. The third one, methodology, specific procedure or technique used. The fourth, result and analysis, finding and the outcome of the research. And the fifth, which is the last one, is the conclusion, to sum up the research. First, we go to the introduction. Okay, introduction. Discrete Fourier transform, which is DFT, is one of the essential tools used in DSP applications. In order to compute the DFT, we can use the fast Fourier transform, which is our project, to prevent the greater number of operations. To improve its efficiency even more in terms of computational speed, this FFT determined using Vedic multiplication was introduced. Vedic mathematics is the ancient Indian mathematical system that deals primarily with Vedic mathematical formula and their application to various branches of mathematics. This project presents a simple digital multiplier architecture based on the ancient Vedic mathematics, which was historically used for decimal system in ancient India, that been proved to be much more effective multiplication algorithm compared to conventional counterparts. For the objective, we have 3 objectives. The first one is to design a 4-bit multiplier by using Vedic multiplication method for FFT. The second one is to compare between Vedic multiplication and the conventional multiplication. And last but not least, to analyze the best performance in terms of speed area between both methods. Now we go to the second section, which is literature review. For the literature review, a computer algorithm, which is a fast Fourier transform, has opened up new avenue for scientific research. The use of the FFT algorithm now effectively incorporates problem-solving methods which were once considered impractical. In determining the discrete Fourier transform, the importance of the FFT is in the reduction of computing time. A direct method of endpoint transformation needs a time proportional to n2, while the FF2 requires a time proportional to n log to n. The approximate ratio of FFT to direct computational time is indicated by the equation below, which is the n log to n equals n square equals to n log to n over n equals to gamma and over n. Okay, we go into a little deep. The algorithm is made up of 12 butterfly structures, each containing one complex multiplication unit as shown in the figure. Thus, the complexity of an FFT algorithm can be generalized as in the bracket n over 2 log to n. Okay, we go basic of the butterfly. A basic 2-point butterfly unit is shown figure above along with the calculation of its output. As you can see, the input is A and B, and how to get the output, which is A plus W and B. And for the B equals to A minus W and B. We go to the section 3, methodology. Okay, for this section, this part, will cover the whole process regarding the method and techniques. First thing first, for each level from half adder until the multiplier was designed in the quarters prime light. Okay, in the methodology, first we have to developing, which is the FFT algorithm. And the second one is simulating. We simulate and run the timing diagram until we get the successful simulation. After that, we obtain the result from the simulation and analyze it. And the last one is comparison. We compare between Vedic and both multiplier. Okay, this one is the Verilog code of the FFT. The left is the Verilog code of FFT Vedic, and the right side is Verilog code of FFT booth. This part Vedic, and for this part we insert the booth module. And this one is the circuit of the FFT, which can be produced in the quarters prime light in the RTL section. Both has same circuit, and the difference is same like the Verilog code, only the module itself. Then we go to the fourth section, result and analysis. Okay, this is a result for the timing diagram of FFT Vedic and timing diagram of FFT both. As you can see, both has a same result. Okay, first let me explain to you all those input and output. Okay, AR stand for the real number, and AI stand for input complex number for A, and BR for real number for input B, BI for complex number for complex number for B input. WR is the real number for the twiddle, and WI is twiddle for complex number, and the output is Z1R, Z1R, Z1I, Z2R, and Z2I. Okay, Z1R for the first output real number. Z1I is for the first complex number. Same goes to the next, Z2R and Z2I. Okay, the important part is the analysis. Okay, from the simulation, we obtain the result that FFT Vedic save up to 39% in terms of the area compared to the FFT booth. As you can see the figure, the graph, the orange one is the FFT Vedic. FFT Vedic contain of 79 total logic element, which is the area, and while the FFT booth contain 129 total logic element, which is the difference is about 50 for the difference. And this one is for the speed. FFT Vedic complete the calculation with 1.01 minutes compared to the FFT both, which is 1.03 minutes, which save up 2%. Okay, 2% compared to the FFT Vedic. Even though the FFT Vedic have a smaller area, which is 79 total logic element, but it can produce much. It can complete the calculation with 101 minutes, which is a bit higher in terms of speed compared to the FFT Vedic, FFT booth. And the last part, we go to the conclusion. So this paper contains 3 objectives that all has been achieved by the end of the research. From the research, it can be concluded that FFT Vedic is much efficient and save more area compared to the FFT booth, as it helped to boost the computation of the FFT while saving up more area, as from the result analysis. And that's to sum up the research paper. Thank you so much for lending your ears for my presentation.